we got Daniel waiting here. Let me let him in. And I think that's it. So Tim.
Ty, I saw your background for a second. It's pretty funny.
Okay.
Good, Danny.
You.
So what we're going to do today is, so yes, Jacob, you started class asking about the Truss calculation. So that's a calculation we're going to start today. Your homework will be to finish it. Today is Tuesday, and it'll be due on Thursday before class. So the nice thing of this block is that things are not due until, you have every other day. The video that I asked you to watch, give me a thumbs up whoever watched it. On the
I don't know which video you had posted because we couldn't access it.
The
I sent
bigger,
an email
biggest?
out yesterday. Did you guys get my email yesterday?
Yes.
Okay, in the email, I put the link. So you should have been able to open that.
It's accessible.
I can send that again. What I didn't have is the document that I wanted you to fill out. So there's definitely, you can definitely have that. Okay. So I will send that again. I actually thought it was, I think after this experience of you building your bridge that you would be more appreciative of what you saw in the video and what we've accomplished as engineers and what we have in our world. Like, we take it for granted that you have bridges, but there were a time when you didn't have bridges and you couldn't cross over. So figuring out how to be able to do that is what that video is all about, and just where we are right now and how big the bridges are. So let's see, what I'd like to do is I'm going to switch things up here a little bit. All right, so just for logistical reasons and so that the video and those that have to go back and watch the video, I am going to mute you all. And I hate doing that because I like the interaction. So if ever you can unmute yourself, that is absolutely fine. If you have a question, please unmute yourself, wave your hand. But I am just going to mute you, so in the event that there is other sound going on around you, as I sometimes have myself, it doesn't interrupt the video going back and forth. But please, by all means, but shut your mute off if you have any questions or if you're not following along. So again, the objective today is to try to go back and review what we talked about with trusses. So I would like to do, we're going to do a shared screen here and remind you of what we did in building this bridge. Prior to the bridge, we calculated, let's see here, where is my, we did some truss calculations, right? So is it not allowing me? Let's see. There you go. All right, you guys seeing the picture of the classroom? Good memories, right? When we first started out building this bridge and what that was like. So there you guys all are, so nice and happy. Right, so in our building of that, Daniel, I think that is your bridge. The challenge was securing it, making everything symmetrical, right? But right away, we recognized, where my mouse is. Okay, the need to put all these trusses in right here, right? So with that, just going straight across, that's not going to be very strong. So when we did this bridge, we learned a lot about how do the forces distribute in there. You can have a tension force and you can have a compression force. Of course, the material matters. So sometimes you were using the bigger wood and sometimes the thinner wood. But with the truss being put in there, we were able to make that piece of wood much, much stronger. Right? So let's see if this will let me click on to our next. All right, Jacob, this was yours. And the reason I pulled yours up, Jacob, is because Blackbaud being down, I'm not able to get everybody else's pictures. You were one of the few that emailed them to me. Oh, who's writing on my screen? Scribbling on my screen. All right, so the reason I wanted to pull up Jacob's is because a lot of you guys had this. When I looked at this on Friday, your end pieces right here, when we take a look at that, had verticals. You were lucky if you had the verticals, but those of you guys that had those horizontals going across. Okay, so what we saw on that with Hayden's, boys. All right. So remember, this gets recorded and I can go back and look at all your chats. So your chats are shut down to only be with me. I can look back at the writings. You can still get demerits. I don't know what they'll do with them, but I'd appreciate some professionalism here. All right, so as we take a look at these,
That's
with
mine.
that being a horizontal line across, we would recognize if I was able to test those, that that's not going to necessarily hold that very strong, as we saw with Hayden's when he brought that in, when Hayden brought his in. All right, so let's see. Put that back up there, clear that all out. All right, so Jacob, there you are looking at your bridge going down. So again, what I had talked about on Friday was if you look at your bridge in that direction, you must see supports on the road going up. All right, Nate, there's yours, very nice. So I tried to get that a clear view so we could look a little bit more down there, but you had a few more trusses going in there, it looked pretty good. All right. And of course, we had ties, which was just crazy and so good. I really hope someday I get to see that in person. That was impressive that you were able to accomplish that. And that was on the bottom view. So then we can have a ton of trusses, right? So with very little trusses, we went from one thing to a ton of them. All right, so what you'll see in the video when you watch it, we go from very, very simple bridges. This was one of the first arch bridges built, called Iron Bridge. All they could span was 30 meters going across, because that's the maximum that you could do with the stone that was going to be placed in there. So something that you all saw as you were building these, right? So here's the Golden Gate Bridge. That was the next challenge, was building that suspension. And this was the Akashi Bridge, that is the biggest bridge that we are aware of in Japan or in the world. Okay, so this is our biggest bridge in the world. And what you definitely see here is the truss system. When you watch this movie, what you're going to find is the radius of this curvature is very important. So going as high as they could here was a challenge, in order that this span and the radius of that curve would work. The other challenge, so you can see all the trusses that are underneath here. It was really, really neat what they ended up doing here to create this bridge to make it work. So one of my favorites, of course, this is built in Japan, is how they kept it from being earthquake proof. And there was an earthquake in Kobe, Japan, that they found that the bridge did pretty good with. So let's clear that off real quick. All right. So I'm going to pause my share. All right, we'll come back to talking about what exactly they did for the earthquake. All right, so I told you that I'm building something to challenge you all. It's taken me a little bit of time, but this is the structure that I'm using. So that's one of the sides. You can see the trusses down at the bottom. This one we got off a little bit, but we did go with an arch right here. So I say we because I have my son help me out here for time's sake, since he's just bored. All right, so something we did here that was really important, that if you go back and look at your bridges, if you hung your road on the inside of that, I guarantee that's where it's gonna break. It's just gonna rip off of there. If you go on the top of it, then you're looking at holding that on top. All right, so this is what it's gonna look like inside the truss system. So hanging those on top of the edges, and then we have this truss underneath the road. right there. So this is where a lot of you guys, you did great on building your sides, but it was building that base that was a challenge. And if you go back and look at your bridge, that's probably where you're going to have your biggest weakness. All right. So what I want to talk about today is, again, how could I go back? If I was building this and I had to do it on paper and I had to make sure this had to stay up, I can't just think, oh, that design's going to work, and then build it and hope that it works and thousands of people die because it ended up collapsing. I need to be able to calculate the exact forces that are going to be on there. Okay, so that's laying on top. Okay. Jack Johns, what does that mean? Okay. Jack Johnson, is that what you did? All right, we are good. So I'm going to go back to here. Unmute you guys. Okay. So you guys should all be unmuted. All right, so those of you that took a look at the movie, some of the challenges, just like we saw with the building, is materials, the weight of the materials, how big they are, and so on. So as we take a look at our trusses, what we're going to do with our truss calculation today. All right, so again, I guess I will email this to you or do my best to try to do that, but I'm going to do the screen share of what that, of the calculation, and we're going to go through and see if we can't figure that out. All right, so let's see. Oh, it's going to be tough having you guys at the end of the day here. You're worn out.
This isn't fun.
Oh, wait till you see what we're about to do. All right, you're going to love it. I know. All right, so again, if you have any question, you may unmute yourself.
This is depressing.
Yeah, I can tell you're so excited. All right, so let's see. I want to do a screen share, pull up our truss problem. Hello. All right, so if you go back to your PowerPoint on the bridge, so again, you might not be able to because that is on Blackboard. This is the problem that I want to set up for today. So I'm going to pause for a moment and allow you guys to all get some paper and pencil, calculator if you don't already have. We're going to begin this problem. Your homework will be to finish it, and this is part of your grade for your bridge. So can you do calculations to tell me how much force is present? Now I chose this design because it's a little bit different in that the angles are not perfectly the same. All right, so we want to go back and try to do the calculations that go with this.
How
So
do we get it to you? Like our work?
I think what you're going to end up having to do is you can scan it and email it to me, so you can scan it on your printer, or you can take a picture
Okay.
with your cell phone of your work and send it to me. Okay, so we can do either one of those. Okay. So I'll keep that up there. So if you could put a thumbs up on your screen when you are ready and you have paper, pencil, calculator. All right, so I'm going to assume that if you care to be doing it, you got yourself some paper and pencil and a calculator. All right, so we take a look at this picture right here. So this is different compared to the one that we did have. The number one thing that we're going to need on this are all these angles. So we're going to need to figure out what this angle is. What is this angle? And so on. Each and every one of these angles.
I don't
So
see
the
a.
first thing,
worksheet.
I
say
can't
that
see the
again.
picture,
Coach,
man.
you don't have the page up.
Yeah, we don't have the page in front of us.
Facts.
It's not
Oh,
showing up
okay.
on your screen?
We're just
No,
seeing
it's
the
just,
file.
We just see your files.
Just your files, yeah.
Oh, really? Okay.
Yeah.
Hmm.
Dang,
All
coach,
right.
guess we can't do it.
Yeah.
No,
All right,
I'll
yeah.
figure it out.
Maybe next class.
Find a way or make a way, Cage.
Maybe next.
Oh.
Let's see.
Y'all are wild.
Hi.
There we go. Is that it?
Can't.
Yeah.
Yeah.
Yes.
No.
Can you email this to us, Coach?
Is everybody seeing it?
Yes.
I'm
Yeah.
seeing the cow, Coach.
All right, now you're seeing it. Thank you for pointing that out.
Coach, can you email this to us after class?
Yes, yes. So that's my goal. My issue is I tried to do it last night in a Google Doc since the Blackboard was out, and it was not, it was making you have to like email me back and get permission to share that with you. Cow, not yet, probably not. All right.
I ain't
so take a
seeing
look
it.
at this. Okay. So our number one thing, I'm going to shut this down. Does everybody, what I would like you to do is draw this, because then I'm going to go back to my whiteboard and work it out on the whiteboard. So you can see the whiteboard. You'll want to make that your biggest part of your screen. So draw those dimensions. So the dimensions that are important is the truss is 6 feet tall. Okay. It is a total length at the bottom of 35 meters. Okay. All right, gentlemen. Pay
Is it
attention.
supposed to be connected in the middle like that? Or is it just bad drawing?
It should be completely connected, yes.
Okay.
You would assume there's width to these pieces, but it would be that these would butt up against one another. Yes. And the 750 newtons is right there in the middle. These supports are at the very tip on the edge, so they're not in by any depth whatsoever.
I'm in a meeting. Go away. Brett, go.
You tell him, Danny.
Yeah, Dan.
True.
Oh, wow.
Oh my god.
Dang.
Yeah.
Wiling.
It was someone. Oh.
Wiling right now. Hey, Ty.
Delete that ish.
I don't even know how to draw on it. So.
My mom see this, I'm burnt.
Yo, what the? Oh, I'm hurt.
Poor Danny.
How do you draw?
Yes. Okay, so we're just going to use SOHCAHTOA. So I'm going to break down each triangle by itself. So the outer truss, you have a triangle that kind of looks like this. Dropping this down, assuming that's 90 degrees. This distance here is 5 meters, and this height, which would be the same as this right here, is 6 meters. So with those two measurements alone, we should be able to calculate this angle right here. If this entire thing is 17.5 meters, then that leaves 12.5 meters here on this side. Knowing 6 and 12, I can find that angle. So first I want you to find these two angles, okay? So I'm going to pause and let everybody try to find those two angles. All right, so those are your dimensions. So again, instead of watching me and copying it down, let's calculate these angles. You work on it, I'll work on it, and then look back up here to check yourself to see what that looks like. So we're looking at this angle right here and that angle. Once I get those two, it's a triangle. So these three angles, I don't need to calculate each of those separately. I can find this entire angle based on that being that these three have to add up to be 180 degrees, right? So let's go ahead. I'm going to call this angle theta and this angle beta. Theta and beta. All right, so if we take a look at the angle theta, I want to look at that angle. This is a right triangle, so we would say the tangent of the angle theta is equal to opposite, which would be 6 meters, divided by the adjacent, 5 meters. So theta is going to be the inverse tangent of 6 divided by 5. Make sure your calculator is in degree mode. And if you plug that into your calculator, I'm getting that angle to be 50.19 degrees. We're going to do the same thing with the angle beta and take a look at what is the angle beta. And you can use whatever letters you want to identify those, but the goal is that we want to identify each one of these angles. So beta is the same thing. We can say the tangent of the angle theta is equal, beta is opposite. So if I come over here, opposite is going to be 6 meters divided by the adjacent side, which is 12.5. So the angle beta is going to be the tangent inverse of 6 meters divided by 12.5. So that one, when you plug that into your calculator, I get that angle to be 25.64 degrees. So our next angle, if you guys can all see that, I'll call this alpha up here. So what we do know is 180 degrees is equal to alpha, like plus theta plus beta, right? Because they are all making up a triangle. So all of those angles must add up to be 180 degrees. So our angle alpha is simply going to be 180 degrees minus theta minus beta. Right? So you should get alpha to be 180 degrees minus 50.19 degrees minus 25.64 degrees. Plugging that into your calculator, well, getting a little bit too low there. Your angle theta or alpha, I get to be 104.17. All right, so how we're doing on that? All good?
Yep.
Any questions?
Nope.
Okay, so once we see that, we can now put that into our big truss, right? So these angles are going to be the same as the angles on the other side. So if I draw the truss to the other side, All right, so I can label these exactly the same. They're going to be all equal to one another. So this one is going to be 50.19. This one is going to be the same thing, 25.64. And that one should be the 104.17. So then the question becomes, when I complete my truss, how much are each of these angles? So for these angles, I'm going to call them 1, 2, and 2, right? Because these two angles should be exactly the same.
Wouldn't it have been easier to figure out like the right of the top in the first triangle? Because then you can just subtract and find 90 for 2, and then you could do the same for 180 or the same for the 90, and then just do the same with the other half.
Are you talking about what I labeled as number 2?
No, so if we found what ended up being like C or whatever, like the top and the first triangle, we found the right side of that, yeah,
Beta, okay.
above that, like in that smaller triangle, no. Yes. If we found that first, then we could have used like common sense to find the other half, and then also common sense to find 2.
True. You would have either way, you would have had to use the tangent function twice. So to find this angle in the right triangle that's here,
Yeah.
you're either finding that angle or this angle. One of the two you have to find. So you certainly.
Oh, I guess you can still find 2 just using, without even doing like the true math.
Correct.
Okay.
So right now that I have these two angles, I'm able to just kind of derive everything else. This one, okay, what we're going to have to do is say these two added together. So beta and beta are both 50.19, right? So what I do know is these are making up a straight line. So altogether, that's going to be 180 degrees. So before I do it, see if you can figure out how much is angle number 1.
I got the answer.
You already got it?
Yeah, but I
All
might be
right,
wrong.
what do you got?
I got like 128.76, but I don't know. I could be
Very
wrong.
good. And I apologize. I said this angle is 50, but it's the beta angle, 25.64 and 25.64. So angle number 1, good. So I'm going to erase this. And we'll go back. I see Sam. If I call that angle number 1, okay, so what we would say is that angle plus beta plus another beta equals 180 degrees, right? So if I want to find angle number 1. So since I know those two, angle number 1 is equal to 180 minus 2 betas. So that's going to be 180 minus 2 times your 25.64. Now, this is all geometry. So Logan, as you're asking, yeah, you could have found that angle and then subtracted 90 from that, or 90 from that angle, and that angle from 90, and gotten this angle, those add up to be 180. There's many processes you could use to find the same angles. But what we now know is angle number 1 is equal to, Sean, you were correct, 128.72
Yes.
degrees. Very good. Now, if I kind of take away the triangles and I look at triangle number 2, these two lines at the bottom of the truss and the top are parallel, right? So if in geometry you have two parallel lines and then you bisect them with another line like that, if I know this angle, then I also know that angle, right? Is that called alternate interior angles?
Yeah.
I think
So
Mr. Bombalski told me something about that.
Right, so if you have two parallel lines and another third line bisects each one of those or crosses through each one, the angle made here is equal to the angle made right here. Because altogether, this has to be 180 degrees on both sides. So if I know this angle, which we call beta, right? So this angle beta is the same as this angle up here. So angle number 2 is also equal to beta. So those angles would also be equal to the 25.64. So we can begin this problem. What is important is that we know all of those angles. And then how do all those angles affect the strength of our truss? Now the past truss, most trusses are equilateral. You have 60, 60, and 60 at each angle. So you have a 60-degree angle, which when you go back to the PowerPoint is the example problem that you would see in there. All right, so anybody have any questions on how we calculated these angles?
No.
Put on all that?
Can't
All right.
you get right now, can you solve for the top ones too?
Well, we just did.
Well, I'm saying the other ones next to those.
Yes, we already knew that one because we saw for alpha.
That's the same
4.
one.
So this one will also be 104.17.
I forgot about
We're
that.
assuming that this triangle on the left is the same as this triangle over here. So all of these 3 angles are the same as those angles.
Yeah.
Yep.
I forgot we did that other one.
No problem. Okay. All right, so I'm going to clean up my board and just write the truss with all these angles in it. And then we're going to begin our calculations. So the question is, what is the tension or compression in each member of the truss? That's what you really want to figure out. So when we go to break our bridges, what is, or take a look at the bridges, what are the tension and compression?
I am.
Okay, so let me try to draw this real quick here so you guys can all see it. I think I need to draw that one a little bit longer. Okay. These markers wear out so fast. There you go. Hopefully those angles look a little bit more like what you have. All right, so what we do know are all these angles, right? So this one is 25.64, 50.19, 104.7, right? 17. So we know all those. This one's 25.64. So you can label all of your angles. Here on each side, and that one was our final one, angle 1, 128.72. All right, so now we go back and we take a look at the forces. So the process in which you are trying to figure out what are the compression and tensions in each one of those. So remember, 3 rules for static equilibrium. Summation of torques equals 0. Summation of forces in the y equals 0, and summation of forces in the x equals 0. So those are your 3 things that have to be true for this bridge to stay standing and not twist and turn and collapse, right? So with those standing up, the first one you want to start with is the summation of torques. So as we take a look at torques, what's important is this bridge is being supported on both sides, right? and then you have weight acting straight down in this part. So we look at this as one object where there are forces on both sides acting up and weight in the middle. So it might be like a bar that looks like this. And then you have two forces acting up. Right? So, the trick of this is what's the video going to look like later, so you guys can all go back and take a look at this. Remember, when you do torques, you choose a pivot point. So the other thing we want to do is we're going to label each one of these joints. So I'm going to go around and I'm going to label them A, B, C. So this is everywhere you'd have a joint, right? Where you would have had to glue pieces together as you built your bridge. A, B, C, D, and we'll call this E right here. Okay, so this is point A, this is E, and this is D. So whenever you do torques, remember you had to pick a pivot point. What point where will it pivot about? So I'm going to pick A as my pivot point, and we're going to put our pivot right here where A is. So torque, recall, is force times lever arm. So how far away is the force from your line of pivot is your lever arm? Remember that you have a clockwise and a counterclockwise torque. So we don't worry about these other members because that compression and tension are inside the object. They're going on internally. The only thing that's going to cause torque is forces that are coming from the outside. So here you have torque is force times lever arm. On our picture, the lever arm of weight would be this distance. I'm going to call that RW. This distance would be the lever arm, R sub D, we'll call RD. So I'm going to call your names out, unmute when I ask you a question. Let's see. Jack Hall. Will weight cause a clockwise or counterclockwise torque at A? So if I hold the bridge at A and I have weight acting down on it, am I going to have a clockwise or a counterclockwise torque?
Counterclockwise.
Counterclockwise.
Clockwise. I was thinking about the resistance. But yeah,
What-
yeah. Never mind.
What's your call, Jack?
Clockwise.
Clockwise. So if I hold this here, if I have a bar and I'm holding it and I pull down on it, it's going to make it want to spin like that, right?
Mhm.
So yes, that's going to cause a clockwise torque. Over here, right? Nate Gleagerman, D is going to cause a
Counterclockwise.
counterclockwise, right? So whenever we do summation of torques equals 0, remember we say clockwise is positive, counterclockwise is negative. So what we would say here is the torque due to the weight is going to be positive minus the torque due to D is going to be negative. It's going to come in that direction, right? Those two add up to be 0. The torque due to the weight is the force of weight times its lever arm. So we'd have weight times R times weight minus the force at D times RD equals 0. So what we're ultimately trying to do here is find what is the force at D. If I can find the force at D, it's going to allow me to find all of the forces in that member right there at that joint. Okay. All right. Looks like we are out of time, looking at my clock. So you can finish solving for the force of D in this problem. You are then going to use that force to come back over here to solve for each force in each one of those, okay, in each one of those members. All right, So I guess I will just stop. What's that?
Wait, what?
Need 5 more minutes.
I swear, it just be going 0 to 100.
Max,
bro.
I'm so lost.
You just got me skied real quick.
Oh, confused now.
Yeah.
Okay, here's what you're gonna do. Number 1, does anybody know, did Blackbaud come back up today?
No, it's still.
It's still down? Okay, so
Yeah.
that's
Can
our
you just
challenge
email
with
us the thing then?
Blackbaud. All right, so number 1 homework is to watch that video on bridges and answer the question of the 7 marbles, the 7 leaps that were overcome to get to the
What does
bridge
that do?
that we see today. Next, then I want you to rework the angles and finish
Rework.
solving for the force. And then I want you to set up free body diagram for D, which means if I'm at joint D, what forces would be present?
Don't know.
We just calculated D, the ground is going to push up on it, right? And then it has 2 members there. You always assume tension. So
What?
we're going to assume that this is going to pull in this direction. We're going to call that force between D and E. You also have a member here, right? So we're just redrawing what you see right there at D. We'll call this one force DC, right? Those 3 forces are the forces that are going to be acting at the joint where D is. The question is, how much are they and which way do they act? So as we saw in our previous calculations when we did this weeks ago in class, obviously DC cannot be acting that way because we need something to act down to counteract force D. But what you will find out is that your calculations will come out negative. So for homework, I want you to solve for
Mood,
these
Jacob.
forces right here. See if you can do that. You don't have to do all of them. For Thursday, I want to see that. So you're going to scan me your work, send it to me, what you think it looks like. Hopefully Blackbaud will be back up and you can look at the example solved. And maybe I'll try. I don't know if I'll have time to scan it and send it to you.
Can you
All right,
tell us
so let me pull you all back up here and see
Wait,
your
forward?
faces. You're all so lost.
You want to see the forces for the free body diagram for D?
For D.
You need to calculate force DC and force DE.
DE.
Mm,
What?
what is going
What's gonna
on?
happen?
Huh?
Yeah, so we got to use the
Oh my
Wow,
goodness,
this
did you guys
easy.
learn anything?
we got to use the numbers and the
Thanks,
Been
DeAndre.
a month since we've done this.
Half of them are letters.
we got to
Elective.
more letters and
Confused.
Elective.
Nobody's,
AP.
yeah, I say weighted. That's my
Okay.
response back.
HA, dude.
Okay, why can I not?
Wait, what do we have to do for the video? You said like 7 things.
The 7 struggles.
7
Or
marbles.
challenges. Oh,
7 marbles.
Like the other video.
That video.
We gotta email you that too.
Okay, hold on.
looking at oop.
What do they do?
35-minute video.
Class over.
Class is over. You have
It's
permission to
retarded, so
sign
we're still
out
on here.
if you would like, but
Not
now
signing
comes
out,
my
don't worry
office
about it.
hours, so I'm happy to stick around and work with you all. All right, but class is over, so.
I just don't.
All right, and the issue is, remember when we did the PowerPoint at the beginning of all this and we had an example? That's in the PowerPoint and it's all worked out. That is on Blackbaud for you to.
Oh yeah, I remember that.
So our issue is that you don't
I have
access
so much
to that
work and I don't know what to look at.
What's that?
I have all this and I just don't know what I'm looking at.
Can we
Look
just
at the
like
bottom.
wait
You
till
got to look at
class
the
on
bottom.
Thursday?
No, I want you guys to give this a try.
You
Okay,
just told us
so,
about A, now we're doing something with D. Like,
Yeah,
okay,
That was
let's
an example.
finish this. So if you guys want to stay.
AP examples.
All right. In this equation right here, we know everything but FD, right?
Yeah.
I suppose.
So we know everything but FD. So all I have to do is get FD by itself. So to get FD by itself, adding that over, you'd have W times RW divided by RD is equal to the force at D. So you're solving for the force at D.
Wait,
So that tells me how hard is the road or the ground pushing back up on my bridge at that point right there. So the greater that span of distance, the more torque is going to be caused by the weight and so on.
oh, so we just plug the joints in and find it?
Say that again?
We just plug them in and then we have FD?
Correct. So what's our weight?
Whoa,
750.
whoa, whoa, whoa.
750 times 5 divided by 5.
17.5.
5 divided by,
Isn't
what's
it?
the next?
Times
12,
17.5 divided by 35.
17.5.
Wait, wouldn't it, what's RD? Wouldn't that be 5 too?
Lever arm.
Okay, no, go back to your picture. How far is? the
Oh,
edge
RD's that whole
away?
length.
It's
Oh,
35.
Is 17.5.
I was thinking it was just from D to the center.
No, it's from A to the center.
Okay.
So that's 17.5.
17 point. So it's 750 times 5 divided by 17.5.
No, no, no. RW is not 5.
RW
RW is this
17.5
whole.
divided by
750 times 17.5 divided by 35.
Wow.
Correct.
Anybody got the answer?
RD is 35.
Answers.
And then is that all we do?
You get FD. That's it.
We have to
That was
find
our
FDE
problem?
too. FDE.
Well, now we want to add it to this. Okay.
Yeah, there we go.
Oh.
That's what I thought.
Logan, did you get a number?
375.
Okay, that's correct. Everybody get 375?
Yeah.
Yes.
Okay.
Can we just do it
Everybody
right
have all this.
Facts.
Can I erase this?
Yeah.
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 Okay.
That's fine.
Everyone that left feeling real stupid right now.
Yeah, facts.
Yeah, let's make the people that
Well,
left.
it's just
mad.
I can
jogging your
sacrifice 10
memory.
minutes of Modern Warfare for this.
Yeah, come on.
Okay, so ultimately, guys, what we are trying to figure out is what is the force everywhere at a joint, right? We want to know how much force is there at each one of these points. So over here, if I just look at D at that point, and I'm just looking at D, I know the ground is pushing up on it. We call that force D. We now know that's 375 newtons, right?
Yeah, that.
There's a piece of wood attached to it that's going to pull on it in this direction. There's another piece of wood attached to it that we're going to assume is going to pull on it. So we always assume that it's going to pull. However, it obviously has to do what? If we know FD is pushing up, this force is going to do what? It should go this way,
Oh, fat.
right? But I'm not going to, well, to keep it symmetrical, I'm going to keep it like that because that fits our picture, right? What we see right there is the exact same thing. Okay. All right. So now the question is, what are these other forces? So remember the three equations, we can use summation of torques, summation of y, summation of x. We already used torques. There's not going to be any torque right here. What we want to use next is summation of forces in the x and y. So summation of forces in the x equals 0. And summation of forces in the y is equal to 0. This is obviously in the x. This is in the y. This one is in
Both.
both. So now is your memory coming back?
How did I do
What
that?
would you do
Yeah,
this-
the whole thing where you do like the,
Find its components.
yeah.
Oh, we
So
have this,
here-
right? Wait, no.
So now what I'm gonna do is break this up into two components. And I'm not gonna look at this, we call that FCD. So this side I'm gonna call FCD in the Y. And this one I'm gonna call FCDX.
What the?
So this is FCDX, CDY. So let's take this triangle and do it off onto the side over here, okay? So we're kind of running, I'm gonna get rid of this again. And I'll blow up this triangle. So we have FCD, FCDX, and FCDY. We calculated that angle to be 50.19 degrees, right? So we do know the angle. We don't know any of these sides, but we're going to try to figure those out. All right, somebody give me an equation for FDCDY.
Sine.
Okay, it's the opposite. That's good. So sine of 50.19 degrees equals what?
FCD or FCDY over FCD.
Very good.
What I said. That's what I meant.
FCDY, opposite,
Okay, Sean.
divided by hypotenuse. So FCDY divided by FCD. So that means FCD sine 50.19 equals FCDY. Okay, now, I see a lot of like heads going up and down very quickly, which means you're just copying down what I'm writing. Make sense of it, then write it down after you've done it yourself. What's the equation for the cosine? That's going to involve
Cosine.
FCDX.
CDX over FCD.
You know what?
With cosine of 25.64. Or no, is it going to be the same angle?
It should be the same angle. So we hit switch over here
50.19.
to E, we're going to switch those.
Should be FCDX over FCD. Wait, so yeah.
That's correct. Cosine of 50.19 equals FCDX all over FCD. So that means FCD cosine 50.19 equals FCDX.
I don't get 100 on this.
Is the whiteboard showing up okay?
Yeah.
Yes, ma'am.
Yep.
Yes.
Then once we find those, so then that's like
Do we have
finding-
FCD?
You don't. So now let's go back. So Jacob, I think you were gonna, now we go back and let's redraw our picture with only X and Y vectors, right? X and Y forces.
Yeah.
So if we go back over here, what does that picture look like? So you draw, you'd have FD, right? Acting up. You'd have
Yeah, no, see though.
the original one, DE. And then you have FCDX. and F, C, D, Y.
Sean, mute yourself.
Oh, sorry.
All right, so set up that picture, your free body diagram in these two equations. And you should be able to, and in combination of these, we should be able to solve for that. So what I'm gonna do is I'm gonna get rid of this up here. All right, so summation of forces in the X equals 0, and summation of forces in the Y equals 0. So look at this picture. Okay, and what do you see? So before I do it, write down the equation in the X and write down what the equation in the Y would look like.
Got it right.
Everybody got those two equations right for that picture?
Yep. Is that it? No.
Well, now we've got to put numbers to it.
Right.
What's the one number we know?
50.19.
We know that angle.
FD. We know
FD.
FD.
We know FD.
We know FD to be
375.
375, which means now I can solve for this, right? So that means FCDY is 375. FCDY is FCD sine of 1.9, 50.19.
Oh, now then we can plug that in back to the.
You have 300, now you're going to work backwards. 375 newtons equals negative FCDY. So that means 375 newtons equals FCD sine 50.19. So negative 375 divided by the sine of 50.19 equals FCD.
I got like negative 488. I don't know if that's right.
I mean,
That's what I got.
488.
Negative 48.
Okay, so, and what does the negative mean when we're doing these calculations? If we get a negative number,
Acting the opposite direction.
excellent. It's actually
Chandler,
acting
you
in the
say-
opposite direction. All right, is it coming back to you now?
Yep.
I would not have been able to do this like without you. This is like the most confusing one we've ever done.
Well, it's been a little while, and it looks very complicated, and it is. It's not easy, But the key is to organize your information, right? All right, so finish up the X.
Wait, so that was for the Y, right?
That was to give you F, well, that gave you FCD.
Well, that Jacob, then you can go back and plug that in to find FCDY.
Well, you'll plug that
We
back
need
in
X.
to find FCDX, which will then give you FDE. So we're trying to find what is the compression or tension in either one of those.
Negative 488 times cosine of 50.19.
Wait, for FCD, do you get negative 488?
Yes, FCD was negative 488. And the negative means it's in the opposite direction.
All right, cool.